Here we are. Welcome to the last lecture of CSC401 Natural Language Computing. In this lecture, we are going to tell a story of the GPT family models. Recently, a member of the GPT family models by OpenAI, ChatGPT, has been extremely popular. So I asked them to help me write an introduction. So in a welcoming tone, write a short introduction for a natural language processing lecture that introduces the development history of GPT models. This is what ChatGPT gives. Welcome to our natural language processing lecture on the development history of GPT models. In this lecture, we will explore the evolution of GPT models from the early beginnings to the current state-of-the-art models. We will discuss the key milestones and breakthroughs that have contributed to the development of these powerful language processing tools. By the end of this lecture, you will have a better understanding of the history and progression of GPT models and their impact on the field of natural language processing. Let's begin. The quality of the text is coherent, but whether the contents make sense is left to your decision at the end of this lecture. So you can decide whether the lecture really covers the developments and their impact on the field of natural language processing in a few minutes. Let's first start with the timeline of GPT models. In 2018, they released the initial version called Generative Pre-Training. In 2019, the second version of GPT was released. And at that time, OpenAI really focused on multitask, unsupervised learning. In 2020, the third version of GPT really made the headline and won the Best Paper Award at NeurIPS. GPT-3 introduced the novel Learn in Context setting. I will elaborate on the in-context learning, aka prompt learning paradigm in a few slides. Later, OpenAI decided to improve the quality of the models based on the GPT-3. They explored two successful directions, InstructGPT and Codex. InstructGPT improves the models on human feedbacks, and Codex trained on both human and programming languages. In 2022, OpenAI combined the technology of InstructGPT and Codex and released the newest member in the family, ChatGPT. Let's first take a look at the structure of generative pre-training. The GPT model really sets the backbone for the GPT family models. The structure is shown in the right-hand side of the slide. A GPT model is a transformer decoder. So it's a unidirectional transformer, meaning that the representation of each token depends on only the token itself and the previous tokens. It's called a transformer decoder because at the time when the transformer was introduced, the transformer authors considered mainly the machine translation problem in a sequence-to-sequence manner. In the sequence-to-sequence manner, you use an encoder to encode the input sequence into a hidden representation and use a decoder to autoregressively generate the output. So in a model, there is the encoder part and an decoder part. The structure of the GPT model happens to be the same as the decoder part of transformer. As an aside, there is another model with the same structure as the transformer's encoder, and the model's name is BERT. But the transformer encoder and decoder can both be used as either encoder or decoder if you use in a proper setup. So I recommend using the name unidirectional transformer and bidirectional transformer because this avoids the name confusion. How was GPT trained? GPT was trained on two objectives. The first one is language modeling objective. You already know that in the previous slides, the previous lectures. And the second one is fine-tuning or multiple tasks. In each fine-tuning, they attach an additional linear layer on top and allow this fine-tuning to optimize all the neural network parameters at the same time. So in this way, the bottom part of the neural network prepares the representations to be ready for classification by the top head. And the linear head at the top handles the task-specific classification. So in this way, when you switch to a new task, you need to train a new classification head to avoid the, for example, negative transfer. This is the common practice for multitask fine-tuning. 1 year later, OpenAI decided that only the language modeling objective is necessary. The language modeling pre-training objective essentially minimizes the perplexity over the token sequences. And this equation shows a minimization of the perplexity. And the perplexity is an average or the expectation over all the tokens that of the entropy. So you try to minimize the entropy or the surprisal as predicted by the language model for each token given by the previous token. So if the language model is trained well, it should be very unsurprised when looking at the new tokens by predicting the new token based on the previous tokens, because it knows that the current token is going to be the correct one. Does this language modeling provide enough knowledge about the task? Some researchers argued yes, and some argued no. The argument towards the positive side is that to model the language, you need to capture the patterns in the language. There are many patterns. Here's one example of the syntax pattern. The number of the subject should agree in the number with of the verb. So when trying to predict the verb, the model already has the knowledge about the subject, because usually the subject comes in front of the verb, and the model should correctly predict that the number of the verb matches the number of the subject. In this way, we can say this language model captures the pattern of the subject-verb agreement. There are a ton of other patterns in the language, and to model the language successfully, the language model is already able to capture the patterns of this type. In this way, the language model stores and can use enough knowledge about the task when they are solving them. But there's a requirement. The corpus really has to be huge in order for the language models to observe sufficient number of patterns. So this is why GPT-2 is trained on a corpus that is around 40 times as large as its predecessor. GPT-2 had a bunch of impressive performance. It reached state-of-the-art on many classification tasks, but on this slide, I want to show you an impressive example. The researchers passed in some prompts or the context that were written by human. And this prompt is about setting the stage for a scientific finding, or this is actually the head for a science fiction story, and let the GPT-2 continue writing the story. So the context is, in a shocking finding, scientists discovered a herd of unicorns living in a remote previously unexplored valley in the Andes Mountains. Even more surprising to the researchers was the fact that the unicorns spoke perfect English. Here's what GPT-2 generates. The scientists named the population after their distinctive horn, Ovid's unicorn. These four-horned silver-white unicorns were previously unknown to science. Now, after almost 2 centuries, the mystery of what sparkled this odd phenomenon is finally solved. Dr. George Perret, an evolutionary biologist from the University of La Paz, and several companions were exploring the Andes Mountains when they found a small valley with no other animals or humans. Perez noticed that the valley had what appeared to be a natural fountain surrounded by 2 peaks of rock and silver snow. I'm not going to continue reading all of the articles because it's very long, and the length is much longer than was shown in this screenshot. This is in page 20 of the GPT-2 paper. Of course, many of the generated contents were hallucinations, meaning that GPT-2 wants to fill in some detailed contents, but the contents do not occur in the real world, like the descriptions about the unicorns. But overall, the quality of the discourse makes a lot of sense, and the sentences are coherent. I want to make another comment about the terminology. At that time, the OpenAI researchers referred to the prompt as context, and there's a difference between calling it prompt and calling it context. If you say context, you expect the model to write a story following the context that you set up. But on the other hand, if you say you prompt a model in a metaphorical term, you are interacting with the model as if the model understands a certain amount of knowledge. To prompt the model to do something, you tell the model to do the tasks that involve more than just writing a story. Here's an example of a prompt-based system. Let's look at one of my favorite examples. This example is in the style of a Winograd schema challenge. And the Winograd schema challenge refers to the pronoun resolution problem. But to correctly resolve the pronoun, you need to have a massive amount of common sense knowledge. In this example, an elephant can't be put into the fridge because it is too large. What is it? To correctly select that it refers to the elephant, you need to know that in reality, an elephant is usually much larger than a fridge. So you can reformulate the selection and the pronoun resolution problem into a prompt-based question. So you put a question, selection, and the answer is into the prompt of the large language model and let this model continue writing the answer directly. So here's what GPT-2 gives. It gives rather random numbers. So it gives rather random generations. It says that I had an elephant in my fridge while eating dinner at a family holiday party with my. So this is borderline nonsense. But another model, GPT-3, DaVinci 3, is able to directly write a elephant. There are a lot of methods to improve the performance of a prompt-based system. On this slide shows a method, learning by demonstration. So in the prompt, before you ask the question, you give a demonstration. It's like providing an example to the student. You give them the contents of another question and provide them with the answer. In this way, you tell this model that you want the answer form to be like this implicitly. And hopefully the model will be able to follow the instruction. and generate the expected answer. Larger language models like GPT-3, OPT, and Bloom are able to follow the instructions in the prompt. And sometimes smaller models like GPT-2 show the ability to learn from the demonstrations in the prompt as well. The example does not need to be very similar to the question. And sometimes the labels in the demonstration does not really matter as well. To select the correct example to be put into the prompt is another research direction that many researchers still have different opinions on for now. And by the way, this setting is called one-shot demonstration. So GPT-3 is able to correctly learn from the demonstrations for a lot of times. And overall, the prediction results are more accurate than many previous state-of-the-art benchmarks. And the success of GPT-3 can be attributed to the high quality of the text data. Training data comes from the text crawled from web. The website data have very low qualities. They are filled with HTML tags. There are a lot of duplicated websites, and there are a lot of colloquial languages. So after removing the HTML tags and removing the duplications, they train a data quality predictor to automatically filter the text. They discarded most of the text. Among the 45 terabytes of text, they preserved only 500 gigabytes and used this 500 gigabytes high quality text to train the 107 billion parameter GPT-3 model. And the resulting model is referred to as Da Vinci. So to further improve the model, it is very, very hard to continue working on the path to crawl internet text data because they almost already acquired all of the text data that were available on the internet. So how to further improve the model? OpenAI researchers collaborated with Microsoft, who has the ownership of GitHub, to train the Codex model. So if you think about the high quality languages, you can think of some features that comes with them. They have correct syntax. They have clear structures. The vocabulary sizes are not very large, and they contain actionable commands. Interestingly, programming languages, as well as their comments and doctrines, fall in the category of high quality languages. And additionally, GitHub contains a massive resource for the high quality programming languages. So OpenAI collaborated with GitHub to train a large model on this code and doc strings. There are 155 gigabytes of doc strings and code. And this size is actually comparable to the size of text data that were used to train GPT-3. So the results were Copilot, and the model's name is Codex, with 12 billion parameters, as well as Code Da Vinci 2, which is a 175 billion parameter model. How well does Codex perform? This is a screenshot from the Copilot official website. You can write the name of the function and write some doc strings that describe what you want this function to do, and let Copilot write the implementation for you. And in this example, the Copilot is able to write something correct. But Copilot does not always write the correct algorithms. And for many times, the programming languages generated by Copilot or Codex does not really pass the test of the interpreter or the compiler. But it is still very impressive that Copilot and Codex is able to sometimes write the correct implementations of the function that you want it to write. Another approach is to fine-tune from human demonstration. Google's FLAN model also follows this path. They collect the prompts submitted to the OpenAI playground and recruit a lot of humans to write the desired generations. They fine-tune the Da Vinci model on this dataset, which is called FeedMe. So the result was a Text Da Vinci 2 model. So the Text Da Vinci 2 model is fine-tuned from the Code Da Vinci 2. So there is a concern. For every single data point that you submit to OpenAI, it can be used as the query to further improve the model. And because OpenAI is actually closed AI, so there isn't too much that we can do to in terms of whether allowing or not allowing them to use the data we submit to the API or the playground to train and improve their further models. Regardless, it takes massive expense and human effort to write the desired generations from the prompts submitted to the playground. Another important component is reinforcement learning from human feedback. The way that RLHF works is that you train a reward model that automatically predicts the quality of the generation and use this reward model to improve your language model, GPT-3, or in the language of the reinforcement learning researchers, the policy. So you improve the language model based on the feedback signals from the reward model. If the feedback signal of the reward model is positive, then you increase the probability that the language model generates these types of high quality generations. And the algorithm is called PPO. PPO was developed several years ago when OpenAI were researching on controlling the robot joint and also applying the reinforcement learning from human feedback to improving large language model is a direction that were also researched several years ago by OpenAI. In 2021, they published a work that uses reinforcement learning human feedback to improve the GPT-2 models. So the effectiveness of reinforcement learning human feedback was not a pure guess. There were a lot of previous works along this direction. Here is a demonstration of InstructGPT. So InstructGPT was the model that was the version of GPT-3 that was trained on the humans demonstration plus reinforcement learning feedback. So the prompt is explain the moon landing to a 6-year-old in a few sentences. Here's the generation by GPT-3. It is able to imitate the format, explain something to a 6-year-old, and it actually fills in several examples out there. But InstructGPT really understands the meaning of explain. He writes, people went to the moon and they took pictures of what they saw and sent them back to the Earth so we could all see them. This is impressive. So in 2022, they combined the technologies of Codex and InstructGPT, applied it to GPT-3 and resulted in ChatGPT. So this slide summarizes a brief recipe for ChatGPT. The backbone structure is unidirectional large-scale GPT, and they were trained on very high-quality text data, as well as coding language. This model was fine-tuned on human demonstration and reinforcement learning from human feedback. OpenAI uses massive engineering effort to put all of this together. And the result is the impressive ChatGPT. So this is an overview of the ChatGPT. In the next few slides, I'm going to describe how the development of large language models, for example, GPT families, will improve the natural language processing systems, and whether the GPT families models are able to solve the so-called general intelligence problem. So there are some ways to build the natural language processing systems. I like to analyze the systems, briefly summarize the systems in terms of the controllability and capability axis. On the x-axis describes the model's capability. The larger the capability is, the higher performances the NLP system is able to reach. And on the y-axis is the controllability. A higher level of controllability comes with more trustworthiness and more interpretability. The classic feature-based natural language processing systems are very stable. They are very controllable, but for many of the times, their capabilities are on the lower end. The embedding-based natural language processing systems have better capability and sadly, less controllability. The deep neural network-based systems essentially replaces the embedding with large neural network. Some examples of the deep neural network-based systems include BERT plus sequence classifier and GPT-2 with sequence classifier. Their capabilities are larger than those embedding-based systems because the deep neural networks can handle the complex mappings in the text, and they're able to capture some higher level dependencies across different entities that are spread around the context. Whereas these kind of things are very hard for the embeddings to capture traditionally. Sadly, the deep neural network-based systems have even less controllability. And even to interpret those deep neural network-based models themselves has been a hot research topic, the network interpretability. So where is the prompt-based systems on this graph? I think the prompt-based systems are here. They start to show some capabilities that exceed the deep neural network-based systems, but their controllabilities are even less. In the future, the researchers on the prompt-based systems could potentially increase both the capability and the controllability. But whether the prompt-based systems will eventually result in the upper right corner of this graph is still unknown. An ideal natural language processing system should be on the top right corner of this graph, but we're still not there yet. Large language models still struggle in many areas. They do not create new knowledge. They can manipulate the tokens and sentences and come up with paragraphs that appear coherent. But in general, they do not create new knowledge, and their factual correctness are very pathetic. So just last week, Stack Overflow announced that they will temporarily block the answers generated by ChatGPT because their factual correctness were just so awful. Large language models struggle at symbolic reasoning. Humans are able to perform very complex symbolic reasonings. But in terms of the large language models, they in general do not outperform the engineered systems on the symbolic reasoning task. Additionally, the large language models do not know about the external world. By external, I mean the real world, the physical world that we humans live in. They can't ground the knowledge onto the external world yet. All the knowledge the large language models have are, in my opinion, on the language level. They know a lot about the language. They know about the syntax, the semantics, and the discourse, but they do not know about the real world. The future research along the large language models need to improve on all of these aspects. Are large language models artificial general intelligences? Absolutely not. Human intelligence is complex and general. And large language models can be useful for automation tools. But previous natural language processing systems can also be used for automation tools as well. Depends on what task that you want to use. There are some trade-offs in the controllability and the capacity, capability. And whether large language models-based systems are the most useful tools is itself subject to debate. And the engineers need to properly choose the correct model and the correct natural language processing system depending on the scenarios. But large language models themselves are not the answers to everything yet. There are many more problems than and the scenarios than those that are suitable for the large language models and deep learning in general. So that's a quick review of the GPT family models and some quick discussions about the natural language processing systems and some of my personal rants of whether large language models are suitable for the future AI systems. If you like this video, please like and subscribe. Thank you.